Welcome to Chemistry, Unit 7, Chemical Equations and Reactions. What are chemical reactions? Well, chemical reaction occurs when the intramolecular forces, so the forces between the atoms within a molecule, of a molecule or ionic structure are broken, and the atoms are rearranged, creating a new substance. So we're going to discuss chemical reactions very frequently in this class. And the important thing to know here is that we're not breaking intermolecular forces or forces between different molecules. We're actually breaking the bonds between the atoms that are holding the compounds together. And those atoms are then being rearranged to create something new. This occurs when the starting substances, which we call the reactants, experience a chemical change and are converted to different substances known as products. So we start with reactants at the beginning of the chemical reaction, and after those atoms are rearranged into different compounds and different substances, we call those substances that result products. For example, this reaction between hydrochloric acid and ammonia produces ammonium chloride, which is a white gas, which you can see here. So this gas didn't exist before, is a new substance, one of the products of this chemical reaction. How are physical and chemical changes different? A physical change only changes the intermolecular forces, causing a change in the state of matter. So an example of this would be ice changing to liquid water and changing to steam or water vapor. So in this example, the tightly packed ice molecules their intermolecular forces are going to break. Therefore, they can slide over each other and create liquid water. When those intermolecular forces between the liquid water molecules gain enough energy, they can turn into steam. But this is not a change in the substance. Ice is solid water. Liquid water is obviously liquid water. And steam is gaseous water. So none of these substances have actually changed. Their phases have changed, that's all. So this is a physical change. A chemical change, however, breaks apart the intramolecular forces and will cause a rearrangement of atoms into new substances. So intramolecular means, remember, within the molecule. So the chemical change here is actually breaking the atoms apart and changing those, rearranging them into a new substance. For example, here's a chemical reaction. Methane gas and oxygen gas create a chemical reaction in which these atoms are being rearranged. So the carbon and the hydrogen here are no longer going to be bonded together. And the oxygen atoms here are no longer going to be bonded together. And therefore we create new substances of carbon dioxide and water. So our products here at the end of this chemical reaction are quite different than the reactants going into that chemical reaction. What are the signs of a chemical reaction? In other words, how do we know that it's taken place? How do we know that there's something happening that's not just a physical change? Well, indicators that a chemical reaction may have occurred include a change in energy, which you might see as heat, either the production of heat or the removal of heat, maybe something getting warmer or colder, or the production of light. Sometimes we can see something burning, or you can see light being produced from a chemical reaction. A color change is an indicator that a chemical reaction has occurred. The production of gas, or the formation of a precipitate, which is a solid particle or solid particles that are formed from mixing gases or liquids together. So these indicate that a chemical reaction may have happened. If any of these occur, it's possible that a chemical reaction could have occurred. That doesn't necessarily mean that that's what's happened, but this is a pretty good indicator that there's been a chemical change. In summary, chemical reactions occur when the intramolecular forces of the reactants break apart and form new products. This is indicated by a change in energy or color, or by the formation of a gas or a precipitate. What are chemical equations? Well, chemical reactions can be described using words. So when we see a chemical change taking place and those atoms are rearranging in a chemical reaction, we can describe that using words. And this is called a word equation. Here's an example. Zinc plus hydrochloric acid yields hydrogen gas plus zinc chloride. And so this arrow here, remember these are the reactants and these are the products, and this arrow shows that there's been a change that takes place. We use the word produces or yields when we're reading an equation like this. A chemical equation is a more specific way of writing a reaction using chemical formulas. So a word equation is one way to write a reaction. More often, we use a chemical equation. So this is the same reaction here. Zinc plus hydrochloric acid yields hydrogen gas plus zinc chloride. But we write this in formulas using the symbols of the elements instead of words. How does a chemical equation describe a reaction quantitatively? Chemical equations also include the number of moles of reactants and products present. So when we're discussing chemical formulas, we also include the number of moles of the reactants and the products so that we can talk about how much of each of those substances is either used up or created. This is represented by the coefficient in front of each formula. So if we write the equation again here, our chemical equation with formulas, we have 1 mole of zinc. This is an understood 1 in front of that zinc since it doesn't have a coefficient in front of it. 1 mole of zinc plus 2 moles of hydrochloric acid yields 1 mole of hydrogen gas plus 1 mole of zinc chloride. So this tells us that for each atom of zinc, molecule of zinc, we need to have 2 molecules of hydrochloric acid. 1 mole of zinc for 2 moles of hydrochloric acid. So there's going to be twice as much hydrochloric acid when we're comparing moles, so not necessarily in mass form, but twice as many molecules of hydrochloric acid than there are of zinc in order to get this reaction to go. So if we look at this in particle diagrams, we'd have 1 atom of zinc plus 2 atoms of hydrochloric acid. And as we know, these get rearranged in a chemical reaction. So these intramolecular forces between the atoms of a molecule within the molecule are going to break and be rearranged. But we're going to maintain the same number of atoms throughout the chemical reaction. So on the other side of this equation, our products are H2 gas and zinc chloride. According to the law of the conservation of mass, mass cannot be created or destroyed. Therefore, particles on the left and right sides of the equation must be equal to each other. So you can see we have 2 chlorine atoms on this side and we have 2 chlorine atoms on this side. We have 2 hydrogen atoms on this side and 2 hydrogen atoms on this side, 1 zinc atom and 1 zinc atom. So this equation is balanced. And none of these particles are disappearing. None are being created in the process of this chemical reaction. There is the same number of particles on each side here for each of those elements. And this is called a balanced chemical equation. How are states of matter represented in a chemical equation? Symbols are used to represent the state of matter for each reactant and product. So this is a particular way to write a chemical equation. We're going to do this frequently, but not all the time throughout the course, because as you get more familiar with some of these substances, you'll understand intuitively which ones are gases and which ones are solids and which ones are liquids. And so we don't need to put that in all of the equations, but you should know how it's written. The represented states of matter are solid, which we designate with an S, liquid, which we designate with an L, gas, which we designate with a G, and aqueous, which we designate with an AQ. Aqueous compounds have been dissolved in water. So these are solutions that have been dissolved in water. We're going to talk more about aqueous solutions later in the course, but generally it is a liquid that's been dissolved in water or a solid that's been dissolved in water, and we designate that as an aqueous solution. So if we were to write the same equation, it's balanced because we now have our 2 moles of hydrochloric acid here. If we were to write this with our states of matter, this is what it would look like. Solid zinc plus 2 moles of aqueous hydrochloric acid yields hydrogen gas plus aqueous zinc chloride. In summary, chemical equations give quantitative information about a reaction, like how many moles of each substance are involved. This shows the law of conservation of mass, whereas word equations only show qualitative information. Why must chemical equations be balanced? Well, we got into this a minute ago, but the relative amounts of reactants and products represented in the equation must be adjusted so that the numbers and types of atoms are the same on both sides of the equation. And we discussed that that is because matter can never be created nor destroyed in a chemical reaction. And in order to keep the law of conservation of mass, we need to have the same number of each type of atom on both sides of the equation. Coefficients, which are the number in front of the chemical formula, may be changed to balance each element. Subscripts, which are the tiny numbers at the bottom of a chemical formula, subscripts in a compound must never be changed, because when you change the subscript in a chemical formula, what you're doing is changing the substance itself, because it now has a completely different arrangement of atoms. So we change the number of each type of molecule by changing the coefficients. We do not change the subscripts because that is changing the actual chemical formula. So how are chemical equations balanced? Well, let's look at our particle formula here for this equation. CH4, or methane, plus O2 yields CO2 plus H2O. Here are our particle diagrams for those molecules. CH4, or methane, we've got 1 carbon atom here and 4 hydrogen atoms. And then we have 2 oxygen atoms, since oxygen is a diatomic molecule. And so we have carbon dioxide on this side, 1 carbon and 2 oxygen, and then we have 1 oxygen and 2 hydrogen for our water molecule over here. So our goal in balancing this equation is to have the same number of each type of atom on both sides of this equation, on both sides of the arrow here. So we start with 1 carbon atom, and there's 1 carbon atom on this side and there's 1 carbon atom on this side of the arrow. So that is balanced. There's no carbon atoms that are appearing or disappearing at any point. There are 4 hydrogen atoms on this side of the equation, and there are 2 hydrogen atoms on this side of the equation. So some of these hydrogen atoms seem to be disappearing, and that is not acceptable according to the law of conservation of mass. We can't have any of these atoms just disappearing. So we're going to need to figure out how to have the same number on both sides. And if we have 4 over here, what makes the most sense is to add 2 on this side and create 4 on this side so that we could be balanced here. But we can't just add hydrogen atoms. So we have to add them with the molecule that they are already in. They're already bonded to oxygen in this H2O molecule. So we have to add a whole nother H2O molecule in order to balance these. So now we have 4 hydrogen atoms on this side and 4 on this side, and that's balanced. But we have 2 oxygen atoms on this side, and now we have 4 oxygen atoms on this side. We can add all of these together because we're taking the total number of oxygen atoms on this whole side, with all of the products totaled together. So we have 4 oxygen atoms over here, and we only have 2 here. So what we're going to do, what makes the most sense, is to add another set of 2 oxygen atoms here. And we're adding those together as one molecule of O2 because that's the way that they are arranged. And so now our balanced equation is CH4 plus 2 O2. We have 2 molecules of O2, 1 molecule of carbon dioxide still, and 2 molecules of H2O. And so you can see here we've changed the coefficients in front of some of these numbers. We do not ever change the subscripts here though, because that would be changing the chemical formula for those molecules, and we would be making some different substance that's not true of what the chemical reaction actually did. So this is our balanced equation because we now have 1 carbon atom and 4 hydrogen atoms and 4 oxygen atoms on the reactant side of the equation. And we have 1 carbon atom, 4 hydrogen atoms, and 4 oxygen atoms on the product side of the reaction. And these coefficients in front of these numbers or molecules here are just represented as 1. They're understood as a 1 if there's no coefficient in front of it. So let's practice this. Practice balancing a couple of equations. It is a bit of trial and error, but here are some tips. Start with 1 element, preferably not hydrogen or oxygen because sometimes those are found in odd numbers and it kind of throws you off. And balance that first. So start with 1 element and balance that first. Then work on another element and continue until all elements are balanced. It may take a little trial and error. So if you're getting frustrated, just know that there is no tried and true method to figure out how to balance these equations. Sometimes you just have to work through it. So our first example reaction is iron plus water yields iron oxide plus hydrogen gas. So starting with an element that's not oxygen and not hydrogen, we've got hydrogen and oxygen here. We have oxygen here and we have hydrogen here. So it makes the most sense to start with our iron. And right now we have 1 atom of iron on this side and 3 atoms of iron on this side. So our first step is going to be to put a 3 in front of this iron so that we have now 3 iron atoms on this side and 3 iron atoms on this side. Now we know that this is going to be a 1, at least temporarily, to make sure that we can balance this. And that gives us 4 oxygen atoms. So we want to try to make this oxygen 4 as well. And rather than changing our subscript here, we're going to add a 4 in front of the H2O formula. So we now have 4 oxygen atoms on this side and 4 oxygen atoms on this side. So far, iron and oxygen are balanced here. Let's see if we can balance hydrogen. We have 8 hydrogen atoms on this side since this is 2 hydrogen atoms and we're multiplying that by the coefficient, which is 4. So we have a total of 8 hydrogen atoms. And in order to get 8 on this side, we're going to need to put another 4 here. Since we have 4 times 2 gives us 8 hydrogen atoms. So now our iron hydrogen and oxygen are all balanced. So this is a balanced chemical equation. So write down these two equations and see if you can balance those two, and then come back and check your answers. Okay, this is your answer for the first reaction here, first practice reaction, and here is your second balanced equation. So in summary, a balanced equation uses coefficients and subscripts to quantitatively illustrate the law of conservation of mass in a chemical reaction. So what are the different types of chemical reactions? There are 5 basic types of chemical reactions. The first is a synthesis reaction, in which 2 or more substances combine to form a new compound, so one new compound. These can also be called composition reactions. So if we use the letters A and B as symbols here of just any substance, if element A, whatever that is, combines with element B into a new molecule or compound where they are now bonded together, that is an example of a synthesis reaction. And here's one in real life. Magnesium plus oxygen gas gives magnesium oxide, which is a solid. And it looks like this, the burning of magnesium and oxygen gas. And that creates a brittle solid known as magnesium oxide. So that makes one compound that's a synthesis reaction. Decomposition reactions occur when a single compound undergoes a reaction that produces 2 or more simpler substances. So think of this as the opposite of a synthesis reaction. We start with a reactant compound, AB, and it divides into 2 separate compounds. It may not be 2 separate elements, but 2 separate substances here from one. So when a battery is hooked up to some electrodes in liquid water, it can actually divide those water molecules into hydrogen and oxygen, and then they combine into hydrogen gas, which is diatomic because hydrogen doesn't just float around by itself, and same thing with oxygen. So this water is being divided into 2 separate substances, and that's an example of a decomposition reaction. Single replacement reactions occur when one element replaces a similar element in a compound. These often take place in aqueous solutions. So if we had 2 substances here, A, B, bonded together, plus another substance, C, that C might replace the B compound or element and give us AC plus B. So it has replaced one of these substances here. And I'm saying substances because sometimes it's an element, sometimes it's a polyatomic ion. And so we need to call them substances because it's not always very clear. I don't want you to assume that it's always going to be one element replacing another, although it often is. And so here's an example. Aluminum plus lead nitrate gives us solid lead plus aluminum nitrate. So in this situation, the aluminum has replaced the lead. Similar elements here, both metals. The aluminum is replacing the lead and is now going to be bonded to that nitrate, and then the lead is out on its own. So that's a single replacement reaction where one of those substances is being replaced. And that happens very frequently in aqueous solutions that involve metals. Single replacement reactions occur in 3 particular ways. First of all, a metal could replace a hydrogen ion. Secondly, a metal replaces another metal, as we just saw. Or a nonmetal replaces another nonmetal. So we're replacing substances that have like properties here. These reactions only occur if the single element is more reactive than the element it's replacing. So we're going to take a look here, but the single element is the one that needs to be the most reactive. So in this reaction, the aluminum, which is the single element, is more reactive than the lead, more active and more interested in becoming part of a compound, more unstable on its own. So it will replace the lead and bond with the NO3, the nitrate. And we represent that in a reactivity series. So this is a chart that's used to determine which reactions can occur, how reactive each type of element is, and therefore whether it will replace another. So if we're looking at these reactivity series, let's identify whether these reactions will occur. They may not. If the single element is more reactive than the one that's in the compound that it's replacing, then the reaction will occur. If it's less reactive, there's not going to be a reaction that occurs at all. So sodium is found here on our reactivity series for metal, and iron is found further down. So this single element is more reactive than the one it's replacing, and therefore the reaction will occur, and we'll end up with sodium nitrate and iron out on its own. Copper and sodium chloride. Copper is found down here. It would replace, because it's a metal, it would replace sodium, and sodium is found way up here. So because the copper is less reactive than the one that it would be replacing, this is not going to cause a reaction. So these elements are not going to react at all. Zinc and hydrochloric acid. Zinc is found here. Hydrogen is found further down the reactivity series. And so the zinc will replace that hydrogen, and we'll end up with zinc chloride and hydrogen gas. Silver is found here on the reactivity series. Magnesium is further up, and so it is not going to be replaced by that silver. The silver is not more reactive, and so no reaction will occur here. These are not something that you need to memorize. You will be given the reactivity series when you need them. Okay, our fourth type of reaction is a double replacement reaction, in which the ions of two compounds exchange places in an aqueous solution to form two new compounds. So whereas we were having one element replace another in a single replacement reaction, now we're having a double replacement. Two ions are replacing two other ions. Precipitates, which are solids, are often found in a double replacement reaction. They're usually a product of double replacement reactions. So in our example here, if we start with one compound, that's AB, plus another CD, we're going to have two elements being replaced here, giving us AD, because this would be our nonmetal ion, so it would replace another nonmetal in the B. So we end up with AD plus CB. This is our metal, this is our nonmetal. So metals are replacing metals, or nonmetals are replacing nonmetals. And here's an example. Potassium chromate combines with lead nitrate, yielding lead chromate and potassium nitrate. So the potassium and the lead both swapped, or we could say the nonmetal ions both swapped with each other. So it was a double replacement. And this reaction between potassium chromate and lead nitrate actually produces a double replacement reaction that creates a yellow precipitate. So you can see that precipitate forming there. Solid compounds being formed within an aqueous solution. And then our fifth type of reaction is a combustion reaction. A combustion reaction occurs when a substance, which is usually a hydrocarbon, combines with oxygen, releasing a large amount of energy in the form of heat and light. And the reason this isn't written in A's and B's and C's and D's is because we're discussing very regularly here having a hydrocarbon and reacting with oxygen gas to create carbon dioxide and water. So we're going to represent that hydrocarbon as C something, H something. And so that's why we have the X and Y for our subscripts here. An example of this reaction would be C3H8, which is propane plus oxygen gas. And you know when propane burns, it gives off heat and light. That's how we heat our gas stoves or gas grills. And so carbon dioxide is given off and water. Combustion reactions, unlike some of these other reactions, are not reversible. In summary, there are 5 basic types of chemical reactions which all follow the law of the conservation of mass. Single replacement reactions will only occur if a more reactive single element replaces a less reactive element.